All right, let me do this too. Okay, yeah, so today what we'll do is we will focus on z-scores, which we talked about Monday, and then we will also work on the homework that is due not until the 15th. I mentioned already that your exam, I'll be posting that later on today, and it's just everything that we've been covering thus far, up through the stuff on z-scores. I noticed in your this step-by-step book about SPSS, it does talk about z-scores, or at least talks about the normal distribution once again in chapter 7 in the version of the book I have. So that's it. It shows also the procedures to go through and do descriptive analyses using the frequencies analysis. So if you can always look at that for a quick reference if you don't want to go back and watch the video if you forgot how to do something. So there is that. Okay, so are there any questions about anything before we get started? Right, okay, so yeah, let me go ahead. I want to share with you what is known as the z-score probability table. Hopefully I can see if I can get this thing to come up. Well, okay. Let me try this then. All right, just a moment. Let me, oops. Okay, now it should show. It should show. Oh, okay. All right. Okay, so everybody should be able to see my screen. It has this probability table on it. It shows this normal curve. Can somebody give me a thumbs up that they can see this thing? Very good. Okay, yeah, so yeah, this is the z-score distribution. This is what we see when we are looking at the probability of some score occurring, but more specifically, what is the area of the curve to the right of a given z-score? Okay, so if we recall that a z-score is standardized, or it means that it's a standardized distribution of scores, so that the mean for z-score distribution will always and forever equal 0, and standard deviations will always equal 1. So because this distribution is perfectly symmetrical, if we look over here, so I'm going to show you how to read this table. If we look over here on this left-hand side, we see z and we see the number 0.0. Okay, so that's indicating the z-score that equals 0 in the table. So that's going to be right there, smack dab in the middle of the distribution. And so what this is indicating, normal curve tail probability, standard normal probability in right hand of tail for negative values probabilities are found by symmetry. I'll explain what that means in a second. But the z-score of 0 indicates that on the right-hand side, so from going 0 to the right-hand side, there is 0.50 or 50% of your distribution to the right. Okay. Because this thing is perfectly symmetrical, that also means that, well, how much of the distribution is below that z-score? Well, it also would be 0.5. Okay, so it's perfectly symmetrical. And so that is one example. Now, if I were to say, okay, what proportion of the distribution would fall to the right of the z-score of 1? We would come down here and we would find the 1 and it's perfect one. So what you have here, this is the first whole number if there is one. Here's the second number past the decimal, and then this is giving you the second decimal place. And so if we want a 1.00, and so we're looking right here, and we find that there is to the right of a z-score of 1, there's about 0.1587, or about 15.87% of the distribution to the right of that z-score. So because this thing is perfectly symmetrical, if we were going to say, okay, well then what is, if a z-score of 1 is like right about here, if we would say, okay, well, what then is to the left of that z-score? Well, it's just the complement of 0.1587. So all you'd have to do to find that, if I would say, what is to the left of that z-score, or what proportion of scores fall below the z-score of 1, it would just be 1 minus 0.1587. And that is 0.8413. So a little bit above 84% then of the distribution falls below the z-score of 1. Okay, so that is true because the thing is perfectly symmetrical. Okay, so if we have, let's say, a z-score of, let me just pick one out here, a z-score of 1.65. Okay, so z-score of 1.65, you come down and find the 1.6 right here, and then go over to where you can find on the top the 0.5. So a z-score of 1.65 would indicate that about a proportion of the tail that is to the right of that z-score is about 0.0495. Or you could round up and say a little bit, about 5% of the distribution is to the right of that score of a z-score of 1.65. So again, where did I find 1.65? Well, I find the 1.6, and then I go over and find the second number past the decimal place, 0.5, and I come over and find this right here. And this is the z-score of, the z-score 1.65 indicates that to the right of that, you would have a probability of 0.0495. Well, what's to the left of that? Well, most of the distribution. So it'd be 1 minus 0.0495. And so that means then to the right of that to the left of that distribution, would be the majority of the distribution. That would be 0.9505. So about 95% of the distribution would be over here. So we're looking at a z-score, just roughly estimating it. Say like that mark right there is 1.65. So what's to the right of that? Well, about 5% of the distribution. What's to the left of it? About 95% of the distribution. Okay, so it's in, and if you have a negative z-score, so if you have like a z-score of -1, you read the table the same way. You're on this side of the distribution. So okay, so z-score of 0, z-score of 1, z-score 2, z-score 3, z-score 4, and so over here would be z-score -1, z-score -2, z-score -3, z-score -4, etc. So whenever you go to the like regular linear numbers, whenever you go to the left of 0, below 0, they become negative. And so if you would say, okay, what proportion of the distribution is below a -1 z-score, it's still going to be 0.1587, or about 15.87%. Okay, what is above that? Again, we get that number of about 84% would be above that. So you'd say, the z-score of -1, right about here. And okay, how much is to the left of that? Well, it would be what that number is indicating. What is to the right of that? It would be everything over here. And so it would just be 1 minus this number would indicate what is left over on this other side. Okay, so that that is how, that's just a few examples of how we would read this table. And you can see how we get to really high z-scores, a z-score of 5. It's indicating that, you know, well less than 1/100th of 1% of the scores are going to be to the right of 5. So 5 would be way out here, where you would have very, very few scores being observed. And so you can think about this like the height of men. You've got, you know, people like, you know, LeBron James or something like that are way out here on the distribution. They're way out here, that there's very, very small percentage of human beings that are taller than that man. So that is one practical or real life example of where a z-score might apply. Okay, so that's the z-score table. Are there any just general questions about the z-score, of where I was getting those numbers from and how you read this thing? So again, you know, z-scores, you want to read this table like, okay, here's my first whole number, here's my first number past the decimal, and then this tells first number, and this is the second number past the decimal. So a z-score of 0.87, for example, it would be like, there's 0.8, and then go over to where it says 7. So that would say to the right of the z-score of 0.87, then you would find about 0.1922 of the distribution is left over, or about 19.22% of the distribution is left over. And then if you want to find, or to the right of it, if you want to find what is to the left of that, it would just be 1 minus 0.1922. So that is 1 minus 0.1922. And that would mean that it's 0.8078. So about 80% of the distribution is less than that, or to the left of that is falling on this side. Okay. All right, and it would be you know, the same if you're doing it negative 0.87. It would be over here, but your answers would be flipped. Okay, so that's how you read this table, and there is a couple exercises where you're going to want to do that. Let me go to the homework here, and let me start with talking about some of these questions on the homework. All right. Okay, so this is your homework that's due on the 15th, and I've got a little I've got the normal distribution here, and it's showing again, here's one standard deviation above the mean, here's one standard deviation below the mean, 2 standard deviations above the mean, 2 standard deviations below the mean, 3 above, 3 below. And this is, if it's a perfectly normal distribution, this will always be the case, that if you go 1 below, 1 above standard deviations, that's about 68% of the distribution. 2 below, 2 above, that's going to encompass about 95% of the distribution. And then 3 below and 3 above, that will encompass about over 99% of the distribution. And so there is a diminishing returns effect here. The further and further you go out in the tail, the less and less of the distribution that you're accounting for, just because of the nature of the curve, because it gets smaller and smaller and smaller on the far left hand side, or the low end of the scale, whatever you're measuring, and a equally smaller and smaller proportion occurs on the right hand side of it. Okay, so for this first problem, I'm asking you for a variable that is normally distributed. Okay, let's pretend that we find a variable that's actually perfectly normally distributed. You don't usually find this in your raw data. You can if you get a very large sample of like the height of men or something like that. But let's pretend that a normally distributed variable with a mean of 3 and a standard deviation of 1. What is the range of raw values for this variable that would encompass about 95% of this distribution? Okay, so for 95% of the distribution, you have to go out 2 standard deviations above and 2 standard deviations below. Okay, and so that means you have to add 2 standard deviations to the 3, and then minus 2 standard deviations from the 3. So so a standard deviation here is 1, and so if you have 2 standard deviations, that's 2, and so if you go up 3 plus 2, so the highest number would be a 5. And then if you go down 2 from 3, 2 standard deviations, that would be a 1. And so 1 to 5, that would be the range of raw values that would encompass 95% of the distribution. Okay, do you guys see where I got that from? You're just, I'm just coming up with these numbers, but I'm just saying that if, let's pretend it's a perfectly distributed bell curve like that, you're going up 2 standard deviations. Well, because the standard deviation is 1 and the mean is 3, so 2 plus 3 is 5, and then if you take 2 away from 3, 2 minus 3, or 3, 3 minus 2 is 1, and so it's 1 to 5. The area under the curve in this case would be marked by the scores of the range of 1 to 5. Okay. And so if it was just a distribution, if you say you want to go out, what would encompass 68% of the distribution? You only have to go out 1 standard deviation, and so that would just be a 2 to 4 would encompass 68% of the distribution. But I'm asking for 95%, so you're going out 2 standard deviations. All right, and so that's the interval that covers 95% of the distribution. Okay, so for the next one, I'm asking what proportion of the distribution lies above the z-score of 1 for a variable that's normally distributed. Well, that's one we just actually did, and so this is a problem. Number 2 is a problem that you would have to go to your z-score table. By the way, all this stuff you can also always Google this to check your answers to see if you're right. There's nothing wrong with doing that. I do that stuff all the time just to make sure, did I do this right? A z-score of 1. Okay, so we did this one already. And what we want to do is say, okay, well, a z-score of 1, let's go back to our table real quick here and say, what scores lie above the z-score of 1? Well, so right here, our z-score is 1. It's a perfect 1.00, and so it would indicate that about the proportion that lies above that score is 0.1587, or if you want to say it as a percent, it would be about 15.87% of that distribution lies above the z-score of 1. Okay, so that's the answer for the second one, where you're going to have to use the z-score table. Okay, and so the answer to that one is 0.1587. Okay, so for this next one, it's asking, what is the z-score that indicates about 10% of the distribution lies above its value for a variable that is normally distributed? Okay, so for this one, we're looking within the table to find the closest marker for 0.10 within that table, because that would indicate the z-score that would mark that 10% is above that score. And so this one, what we want to do is let's go back to the table. Okay, and so what we want to find is the closest number that we can find to 0.100 that's saying to the right of the table. So here's the proportions they're getting. They're not going to get any bigger in this chart than 0.50. So here's the biggest, and down here's the smallest. So you can see, you can go down here and find that the closest one to saying that about 10% or a proportion of about 0.10 is to the right would be right here. here it is. And so we can come across, so we're doing this, this is like the reverse of what we just did. We find it within this table here and we go, okay, that means that z-score is 1.28. It's the z-score of 1.28 is the z-score that indicates about 10% of the distribution lies to the right of it. Okay, so for that one, if you see problems that are asked, they're giving you already, they're not giving you the z-score, but they're giving you the proportion of the table that lies either to the right or the left of some z-score. If you know the proportion that lies to the right or left, all you got to do then is find that proportion within the table and then look to see what z-score indicates that. So in this case, the closest one to 0.10 is 0.1003. And so we look over and say, okay, that lines up with 1.28, 1.28. Okay, and so so the answer for that one is the z-score of 1.28. Okay, so I'll mark that. Yeah, so for this one, it's 1.28. Okay, so this one, you guys can help me with this one. What is the z-score that indicates the 50th percentile on the normal distribution? Somebody yell it out. What is the z-score that indicates that the 50th percentile? So right smack dab in the middle of the distribution. What is that z-score?
Is it 0?
Absolutely, very good. It is 0. So right. So if we go, let's go look back at the table and see where that came from. Yeah, so z-score of 0, if you look here, it's saying that 0.50 or 50% falls above it, 0.50 falls below it. And so that is, so the 50th percentile, like you hear about rankings where people rank, what percentile they rank in. That's another application of z-scores. So somebody who has a z-score of 0 in some distribution of test scores or measure of height or running speed or whatever it is, if they have a z-score of 0, that means they're exactly on the average. They're right there in the exact middle. So the other thing, just to think about this, with z-scores, because they're standardized, the standard deviations are always 1. If you have a standard deviation that is a positive 1, you know automatically that that score is above average. If you have a z-score of -1, you know automatically that indicates a score that's below average. Okay, and so, and likewise, it's going on out. If you have a z-score that's 0.5, that's a little bit above average, and then -0.5, again a little bit below average. Okay, so that's that. So okay, let me go back to. Yeah, so that would be the z-score of 0. Okay, so for number 5, what is the percent of people who did worse on a test than someone who got a z-score on the test that equaled -0.20, given that the test the test distribution is normal? Okay, so what percent of people did worse than a z-score of -2? All right, well, there's a negative in there, but remember, don't let that negative throw you off. It's a perfectly symmetrical table. So if we want to go back to our table and take a look at this. Okay, a z-score of 2, exactly 2, And so if this is, so this is marking it as positive. So this would be a 2 on the positive side, but it's going to be the same thing on the negative side. So who did worse than this? So who is to the left of this? What percent of people are to the left of this? It would be this proportion. This is written in proportion. So 0.0228, to read that as a percent, it would be 2.28% of people would have done worse than that person that got a z-score of -2 after you've done the conversion. Okay, so it would be so the percent of people that would do worse on a test than a -2. It's the same thing as saying a +2. You're just, you're just on the negative side of the z-score distribution. And so that means then the answer for that one is 2.28%. All right, so let's go back and do that. So 2.28%. So yeah, if you got a -2, you have a negative equivalent of a -2 z-score given a distribution of test scores. Yeah, you didn't do so well. Likewise, though, if you got a +2, that means in z-score terms you did very, very well. Only about 2.28% of people did better than you. Or you could think of this as the probability of someone doing worse than a 2.0, given repeated testing, is about a probability of 0.0228. Likewise, the probability of someone doing better than that would be about 0.0228. That's the other way that you can interpret these things. Think in terms of probability, about making predictions over repeated testing, what you're likely to find given a large sample of data. So much of this stuff really is based on all these statistical assumptions that you have a very large representative sample of the population you're interested in talking about. And so we'll talk about this later, but in statistics, the most important thing oftentimes when you're doing statistical analyses is that you just have a very large sample. Once you get to a very large, you get up, a lot of times when you see these political opinion polls, they have a sample size of about 2,000 people. And that you don't really have to have much more than that, it turns out, than to get a good inferential, confident conclusion about inferring from the sample to the larger population. So attitudes towards president's performance or whatever it is, towards Congress. You don't have to interview everybody in the country. You just have to interview a representative sample of about a couple thousand people. And at that point, you've hit the point where you're going to be pretty close to what the population thinks, and that gathering more data is just really diminishing returns. You're not going to find, if you gather 2,000 more people, you're going to get a radically different response. So you pretty much have nailed it. You've got your thumb on the pulse of how people feel about certain things. Okay, so for this next one, we are going to be using SPSS to calculate this. And so I said in this class, there's really very few, if any, times that you actually have to do any arithmetic by hand. You don't have to do it here either. I'm asking you to use SPSS to do this for you. So you don't have to calculate by hand what the mean, median, mode, and standard deviation are. We can use the computer to do the math for the z-score for us. So this is what I'm asking. The following are raw z-scores for 10 individuals on an item that asked about favorability towards President Trump. The question asks, how much do you agree of Trump's job performance? And this is just a basic Likert item. 1, strongly agree, to 5, strongly disapprove, to 5, strongly approve. And here are the raw scores. So then you would have the middle scores in between of 2, 3, and 4. Okay, and so what we want to do here is just plug these values into SPSS, which I have to just a moment here. Let me open up SPSS and we'll do this. Okay. Oops. Let me escape out of here. I've got to. No, can't do that. Just a moment. Just 1 second, folks. I'm waiting here for SPSS to open up. It was got closed out for whatever reason. Okay. All right, we should be in business now. Okay, so oftentimes when you open up, at least every time I've opened up SPSS from that Apps Anywhere link, it always defaults to the variable view. So to input data though, we want to be on where it says data view. So we clicked over where it says data view, and we need to punch in these numbers in here for our raw scores that we got from a survey of just a few people in terms of their attitudes towards Trump's job performance. Okay, so I need to go back and remind myself what the numbers are. So we've got, here are the numbers. We need to punch in 1,155,33342. So I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, just double checking. Yeah, there are 10 numbers there, so we have to punch those in. I'm just gonna 1,155,33342. Okay, so I want to just punch those into the Excel spreadsheet, or sorry, the SPSS spreadsheet. 1, 3, 3, 3, 3. And what are my remaining numbers? Somebody help me. You might know. I can just look back at the screen.
There's 2 5s.
2 5s.
Yeah, and then 1 4 and then 1 2.
Thank you, Elizabeth. Okay, yeah, so it doesn't matter what order you put them in, folks, not at all. Okay, so here are our values. And what we want to do is it's asking for you to report on the mean, median, mode, and standard deviation for these. And so to do that, we just, after you've had this punched in, you don't need to mess around with labeling this or any of that stuff. Just go in and where it says Analyze, Descriptive Stats, go to Frequencies. And this is the variable var, whatever, 0001. Go ahead and put that over there. And then we want to make sure to go over where it says statistics. And because this is not automatic, you have to request. I want all these measures of central tendency. I want the mean, median, and mode. And I want to come down here, and I also want the standard deviation. And I guess it doesn't ask for this, but we can always also request the minimum and maximum values for this thing. And go ahead and hit continue and hit OK. Okay, and then let me go and grab this thing. Okay, so here's your output. Okay, and just make sure that you did this right. Yeah, you're looking at, this is the syntax. This is what you asked for, and this is valid cases 10. There's 0 missing. And so the mean here, the average score is 3. The middle score is 3, and the mode also happens to be 3. And so the answer for all of those happens to be 3. Didn't have to turn out like that, but just because of the numbers, well, yeah, actually it did. So it's that for the answer each one of those, it's 333. The standard deviation here is 1.41421. Now, usually you only have to go out 2 places past the decimal, so we can just say the standard deviation is 1.41. Okay, that's fine for the standard deviation. Okay, and so now what we have to do is take a look at the next part of this assignment, and let's go back to it. Okay, so the answer for all these is 3, 3, 3, and 1.41. Okay, so then on part E, I'm asking you to convert the highest score into a z-score. Okay, so if we recall that our z-score formula is this, it's the raw score, so the highest score here would be a 5, minus the average score, which is a 3, divided by the standard deviation. So in this case, it would be 5 minus 3 divided by 1.41. All right, so if we go, let me stop sharing this for a second and then go and let me open up. I'll just put this in Google. Let me go back to, all right. Okay, so we got, put this in parentheses, 5 minus 3, it's already up there because I was doing this previously. 5 minus 3 divided by 1.41. All right, so if we go ahead, you can type mathematical equations directly into the Google search bar. Yeah, you can do that, and then you don't have to bring up a calculator. You go ahead and do that, and so it reveals that the z-score here would be a z-score of 1.418. All right, so that's the z-score for the highest value, and then for the lowest value, and you could round that up. You could round that up to 1.42. That would be the z-score. Because really, in the social sciences, we can't be kidding ourselves. We can't get past much the second decimal place. It's not physics here. We just don't have the precision. So there's really no good reason to be reporting past the second decimal place, because the things that we're trying to measure, they're so soft and squishy anyway that we can't really justify getting down to the third or fourth decimal place. I mean, they do that in physics all the time. They have to, but in the social sciences, we just don't. We're kidding ourselves, and we think we can be even more precise than that. So we can just say, it's 1.42. That's the answer. All right, so if we want to do for the lowest score, we just change, the lowest score in here is 1. So where does that fall? What z-score distribution does that give us? So again, we just go, the raw score, which in this case is 1. Also, then we want to subtract from that the average score, which is 3, and then again divide by the standard deviation for the distribution, which is 1.41, and we do that. And this turns out to be exactly the same z-score, but it's on the other side of the distribution. It's on the negative side, so it's negative 1.42. Okay. All right, and so that is, and I have to actually break a little bit early today. I'm going to just go back and fill this in. So the z-score for the highest would be, oops, what is it? It's changing my 1.42, and I lost a letter somehow. And then the lowest one, it would be negative 1.42. Now that negative is important. Just because it's the same number, don't neglect the negative, because that's very useful information. That tells you that if it's above or below the average, and so that's crucial to not forget the negative sign. But that's it, folks. That's the homework. And so I'm going to go ahead and turn you loose on this. If there are questions, please ask me. If there are things that any additional things that you're not just quite grasping yet in the class, you really want to show up to the Friday homework sessions. The class is not going to get any harder in terms of the amount of homework I give out. It just is going to get a little bit more complicated in terms of interpreting the output of SPSS, especially when we get into some of the later stuff. So you really don't want to fall behind because it's one of these things where each thing builds on the other thing to some degree. But yeah, it's one of these things where if you're questioning, you're not sure, really you want to come to the homework sessions on Friday. But yeah, I will have the homework, or not the homework, the exam. I will have the exam to you later on this evening. I'll give you a notification about the exam. It should not be any surprises whatsoever what you're doing. You will have to do some SPSS procedures on the exam, very, very similar, pretty much identical to what we've done in class so far. I'm just giving you different variables to work with, and then there is a couple of them where you just have to punch in values like we just did and to find things. And so find things in the output, identify the correct things you're supposed to be looking at in the output and reporting back to me. But that's it, folks. That's all I got for today. So if there are any quick questions, I can take them now. But if there's something that you want to ask me about, that it's generally just some procedure in SPSS, I encourage you just to come to the Friday sessions, because if you have a question, that means at least probably some other person in the class has the same question. But that's it for today. So you are good to go. And I'll send out that invite and that notification about the exam, which should be posted later on today. Okay. All right. Bye-bye. Have a good one.